here we have, if you can see over here, we have a region of where the value of the wave function is 0. And since the probability density is given by the wave function squared. So that means the probability density is also 0 at that point. So that means, so this corresponds to our idea of a radial node, like no electron density there. Also, what you might notice is that the value of the wave function becomes negative. So this is why I drew them in different colors, right? Because these two like parts of the orbital have different signs. But when we take the wave function squared, everything becomes positive. So it just looks like this. So again, we have these two, oh, sorry, that should be like that. It should be like, this is a different function. It should be like this. Okay. So this shows that we have two regions of electron density. So which corresponds to our two parts of the orbital. Now there's one final thing I want to talk about. So this is like the idea of like the radial distribution function. So right, so these graphs show that the value of the wave function is like approaching infinity at the nucleus, right? But this makes no sense, right? Because how can like the probability you find something be like infinity right there at that region? Like that would imply that the electrons are only at the nucleus. Well, the problem is that this describes like a particular like point in space, that radius from the nucleus, and the area around the nucleus is smaller, right? Like if we imagine a sphere with some small radius around the nucleus, it has a smaller volume than like some distance away from the nucleus. So when we take that into account, the actual like probability of finding an electron somewhere at a given distance from the nucleus looks more like this, right? So that's for the 1s. And then I'll pick a different color for the 2s. Okay. So it looks more like that. And again, with the 2s orbital, we still have this area of 0 electron density. Okay. So one thing I want you to note is that if we look at the area with the highest electron density and the areas with the highest electron density, we'll see that the 2s orbital has more electron density far away from the nucleus. And the 1s orbital has a maximum like density at a small radius from the nucleus. So if we go back to the images I have, you can see that indeed the 2s orbital is drawn like smaller than the 1s orbital, right? Does that make sense? Okay. So before I start talking about the p orbitals, do we have any questions about what I just covered? No? Okay. So let's start talking about the p orbital. So for a p orbital, L equals 1, right? So how many angular nodes are in a p orbital, right? So we should expect to see one angular node. Okay. So if I draw a p orbital, it looks like this, right? And then that's our angular node. So when I draw the wave function for this orbital, and then radius, it kind of looks like this. So again, we have zero electron density at the nucleus, right? But we have this area where the wave function is positive and this area where it's negative. So this is why we draw the p orbital as like one lobe is shaded and one lobe is unshaded. This orbital is unique in that it's really the only orbital to have non-zero non-zero value of the wave function at the nucleus, which means that this is what we call this, like, it penetrates into it penetrates like more of the inside of the atom. And so d orbitals have two angular nodes. You don't really need to know the shapes of the d orbitals. They look like, if I draw an x, y, z axis, so this is the x-axis, this is the y-axis, and this is the z-axis. So one of them is like a lot. So one of the orbitals is in the xy plane, and it has lobes along the x and z axes. And so this is the x squared minus y squared. Actually, it might be easier to just show you a picture instead of me trying to draw them. So as you can see, yeah, along the x and y plane, we have the x squared minus y squared orbital. And then, so in the xy plane, but not along the axes, it's the xy, xz, yz, and then the z squared. But this isn't filling apart. And then the f orbitals have even more complex shapes, which I can try to show you. So the f orbitals here, so they have even weirder shapes, and this really isn't super important. Okay, so now we have all of these orbitals, right? But now our goal is to put them in order of increasing energy. Because when we go to fill these orbitals with electrons, the orbitals with lower energy will fill first, according to the Aufbau principle, right? So there are some like inconsistencies with this filling order, because especially like as you go down the periodic table, the orbitals start to become very close in energy, and other effects are also important, such as like exchange energies and other stuff like that. So it's not super, but yeah, this is filling order is like pretty good. So, and because of this filling order, we have the structure of the periodic table. So, okay. So the order, as you can see, so we start, can you see my mouse? So you start up here, and so first we fill the 1s orbital, then the 2s, then the 2p, then the 3s, and the 3p, then the 4s, and you just keep on going, right? Okay, so this might seem hard to remember, but luckily there is a rule. So it's the Madelung principle, right? So this states that you want to fill orbitals in order of L plus n, right? So, so for example, let's look at the 2p, right? Okay, so this, it's not super exact, but for example, let's look at the 2p. So can someone tell me the values of L and n for the 2p orbital? So n is just the big number in front, right? So n equals 2. And as we saw before, all the p orbitals have L equals 1. So L plus n equals 3. So then for the 4s orbital, this just as an example, we have n equals 4 and L equals 0. So the total is 4. So since 4 is greater than 3, we fill the 2p6 before the 4s2. Also, there's Hund's rule to talk about. I think I'll have to draw this since it's, let's talk about, for example, the 2p orbitals, since they're easy to deal with. So can someone tell me how many 2p orbitals there are? Does anyone remember? Okay. So 2p. So for the 2p orbitals, we have L equals 1. So M sub L equals -1, 0, and 1. So we have 3 orbitals. And then 3 orbitals, which combined hold 6 electrons. So I'll draw, so often you'll see orbitals represented as boxes. So I'll do the same thing here. Okay, so let's say we need to fill these orbitals. So what order do we go in? Okay, so all of these orbitals are the same energy. So they're what we would call degenerate. So we can just fill any one of them. So, okay. By the way, so each half arrow represents 1 electron. So then if we have this represents a +1/2 spin. And then this represents -1/2 spin. Right? Okay. So now, remember that electrons are all negatively charged. So that means that they actually repel each other, kind of. So we don't want to put electrons in the same orbital unless we have to. So when I go to put in a second electron, we have to put it in a different orbital. And for kind of complex reasons related to quantum mechanics, like if you want, you can look up what's called exchange energy. So basically, for all of these like half-filled orbitals, all of the electrons will have the same spin, right? So if you notice, I drew both of these electrons having a +1/2 spin. Does that kind of make sense? Okay. So then we fill the third one, and then it has to, and then we also make that +1/2. Okay. So now we can't just put an electron in its own special orbital, right? We have to start pairing up electrons. So if you remember the Pauli exclusion principle, we can't have these electrons have all of the same quantum numbers. So that means when we could put a second electron, in this orbital, it cannot have a +1/2 spin. It has to be a -1/2 spin. And the same follows for all of these, right? Okay, and as you can see, we have 6 electrons. So a good analogy for this is like, okay, so imagine the electrons are people and they're getting hotel rooms, right? So we won't put 2 people in the same hotel room unless we have to. So we'll try to spread them out, and then if we have to put them in the same hotel room, yeah, that's that. Okay. Does anyone have any questions on the filling of orbitals? Oh, so the idea of these electrons, like the electrons wanting to go into their own orbital, is called Hund's rule. Okay. So let's try to explain like the shape of the periodic table. So let's look at this diagram. Which orbital is the lowest in energy? Can someone write in the chat? So according to this diagram, we know that we fill the orbitals with the lowest energy, right? So that means since we fill the 1s2 or we fill the 1s orbital first, it's the lowest energy. Oh, by the way, so see these little numbers on top? So that just tells you how many electrons there are in those orbitals. So this is just the 1s orbital. It's not the 1s2 orbital. It's just that just says you can fit 2 electrons there. So with that in mind, so as you might imagine, when we fill the first 2 orbitals, when we have the first 2 elements, okay. So if you remember, so the atomic, just as a throwback, so the atomic number is determined by how many protons there are. So this little number here, right? See the number on top of all the element symbols? So that's the atomic number that tells you how many protons are in one atom of that element. So in order to make everything neutral, we have to have an equal number of electrons and protons. So an element, so one atom of scandium, for example, it has 21 protons. So how many electrons do you think it will have? 21, right? Okay. So hydrogen, we have 1 electron. So that means we put 1 electron into the 1s orbital. So we'll write its electron configuration as this, which is 1s1, right? Okay. Then for helium, now we have to put in 2 electrons. So since the s orbitals are not completely full yet, we can just put them in there. So we'll write the electron configuration as 1s2. Right. Okay. So let's move on to lithium. So now all of the 1s orbitals are now filled, so we can't put any more electrons into them. So what's the next orbital we can fill? So can someone look at this diagram and tell me what's the next orbital to fill?
2s1.
Yep. So, yep, that's correct. So for lithium, we have, so remember the 1s orbital is still filled, so we leave that there. But now we have 2s1. So then what do you think, can someone tell me the electron configuration of beryllium?
2s2.
Right, but you have to leave in the first part, right?
1s2.
So it's 1s, yeah. Okay, yeah, so you're right, 1s2, 2s2. So now the 2s electrons are filled, right? Because if you remember, we can only fit 2 electrons into the s orbitals. So now we move on to boron. So B, the most boring element. Right. Okay, so let's look at the diagram again. So what's the next orbital to fill, right?
2p6.
Right, okay. Yep, that's right. But just remember, it's not called the 2p6 orbital, it's the 2p orbital, and the 6 only refers to how many electrons are in it. Got it?
Yeah.
Okay. So, yep. So we keep everything the same. So 1s2, 2s2, and then yeah, 2p1 because it's only 1 electron. So then I'll give you all a second. So try to figure out what neon is. So.
1s2, 2s2, 2p6.
Yep. So that's right. So, okay. So as you can imagine, when we start getting to like the later elements, these electron configurations get very long. So we need a way to abbreviate them. So what we do, okay, so this group of elements is called the noble gases. And okay. So the idea is that so the noble gases have filled all of their, have basically just filled their orbitals. So then let's say, so we can abbreviate this as Ne, right? Okay. So just one more example. Let's do phosphorus. So how about you all try to write the full electron configuration of phosphorus? Like just write it on your own piece of paper. It's too long to say out loud. Oh, by the way, this stuff is in the AP curriculum, so this stuff is important. Oh, and here's the filling order. Okay. Well, it's hard for me to show both at once, so I'll just write it down, and you can review this. You can review the order later. There's probably a million ways to remember this order. Okay, so it's going to be 1s2, 2s2, 2p6, 3s2, and then 3p, and then 1. So 1, 2, 3. So 3, right? And then I want you to notice that this is the same as this. These are the same. So we can abbreviate phosphorus as neon plus 3s2, 3p. Does that make sense? Okay. If we don't have any questions, we'll take a 10-minute break. Is that okay?